All right, let's go on a little journey today. But we're not heading to some faraway country. We're going somewhere way more fundamental, the number line. You know, that infinite road we all learned about in school? We're going to think about numbers not just as symbols on a page, but as actual places you can visit.
I mean, think about it. You use numbers constantly. For counting, for measuring, they are literally everywhere. But if I asked you to gather up all of them, every single one, what would that even look like? What are they really? Well, that's the big question we're diving into.
So, to figure this out, let's imagine we've got a bag with us. We're going to take a walk down this infinite number line, and every time we find a new type of number, we're just going to scoop it up and pop it in the bag. The goal? To collect them all.
Okay, our journey starts at the very beginning, with the most basic numbers you can possibly imagine. So get your bag ready.
First up, we've got the ones you learn to count with, the natural numbers. So, in the bag they go. 1, 2, 3, and on forever. We'll call this set N. Then, oh, wait, we missed one. Let's grab 0. Now our bag has the whole numbers, or W. And of course, we can't forget the other side of the line. We scoop up all the negatives. And just like that, we have the integers. We call this set Z, which comes from the German word zahlen, which just means to count.
So, our bag's got all the whole numbers, positive and negative. But as we're walking down this line, you can't help but notice there are huge gaps between them. I mean, what about all the space between 1 and 2? It's time to start filling those in.
The numbers that live in these gaps? They're called rational numbers. And honestly, the name is a massive clue. Rational comes from the word ratio. So a rational number is, simply any number that you can write as a ratio, or a fraction, of two integers.
So we start grabbing them and throwing them in the bag. 1/2, -3/4, even decimals like 0.875, which is really just the fraction 7/8. And wow, okay, it feels like we're really filling up the number line now. The gaps are disappearing.
But hold on, what about a weird number like 0.333 repeating forever and ever? Surely that can't be a simple ratio, can it? Well, check this out. With a little bit of algebra, we can prove it is. If we just say x is our repeating decimal, and then we multiply it by 10, we get 3.333, which is really just 3 plus our original x. A quick little shuffle, and you solve for x, and boom, it's exactly 1/3. So yeah, even those infinitely repeating decimals fit right into our bag of rational numbers. Okay, our bag is definitely getting heavy now. We've got all the integers, and we've collected all the fractions and repeating decimals in between them. But this is where our journey takes a really unexpected turn.
Let's just stop for a second and ask ourselves a really important question. Is our collection complete? Is every single point on this number line accounted for now? I mean, it sure feels like it should be, right? We have fractions of fractions of fractions. There can't possibly be any space left.
The answer is a pretty shocking no. It turns out that even after you've collected every single possible fraction, the number line is still absolutely riddled with an infinite number of tiny invisible gaps. Our bag is nowhere near full.
So what on earth is hiding in these gaps? To find out, we actually have to go way back in time, back to ancient Greece, where this whole discovery was treated like some kind of dangerous, forbidden secret.
See, around 500 BC, you had the Pythagoreans, and their entire philosophy was built on this really beautiful idea that everything in the universe, from music to the stars, could be explained by whole numbers and their ratios. But then, one of their own guys, Hippocrates, stumbled onto something that threatened to bring their entire worldview crashing down. And it all started with something so simple, a square with sides that are just 1 unit long. Using their very own famous theorem, they figured out the length of the diagonal, and that length is the square root of 2. The problem was, no matter how hard they tried, they just could not write this number as a simple fraction. It was impossible. This thing, the square root of 2, was something totally new. It was irrational. It couldn't be expressed as a ratio of 2 integers. It was a completely new kind of number that was living in those tiny gaps between all the fractions.
And yeah, the name says it all. The reason they're called irrational is literally because they cannot be written in the form of a ratio. I mean, for the Pythagoreans, this discovery just completely shattered their neat and tidy mathematical world.
This idea was so revolutionary, so earth-shattering,
that the legend actually says the other Pythagoreans took Hipparchus out on a boat and drowned him, just to keep the secret of these irrational numbers from getting out. I mean, that's how big of a deal this was.
So how can we spot one of these irrational numbers today? Well, the telltale sign is in its decimal form. A rational number is predictable, right? Its decimal either stops, like 1/2 is just 0.5, or it repeats a pattern forever, like 1/3. But an irrational number, its decimal is a totally different beast. It goes on forever without ever repeating. It's just an infinite, non-repeating, completely patternless string of digits.
And these crazy numbers pop up in the most ordinary places. That diagonal of a square gives us the square root of 2. The ratio of a circle's circumference to its diameter gives us pi. These famous patternless numbers are absolutely everywhere, filling in all those invisible gaps on our number line.
So we've found them. We've found the secret numbers that were hiding in the gaps. Now let's get them into our bag and finally complete our collection.
So when we take our bag, which already has all the rational numbers, and we add in this whole new group of irrational numbers, we finally have the complete set. This whole shebang is called the real numbers, and we denote it with the letter R. A real number is either rational or irrational. That's it. There's nothing else.
And with that, our journey is done. The number line is finally, actually, truly full. Every single point, with no gaps left whatsoever, corresponds to a unique real number that we've collected in our bag.
This perfect one-to-one match was all formally proven back in the 1870s by two mathematicians, Cantor and Dedekind. They're the ones who show that the set of real numbers and all the points on the number line are a perfect, seamless match.
So we did it. We walked the line and collected every single real number. But it does make you wonder, doesn't it? We filled this entire one-dimensional line, but could there be other kinds of numbers? Numbers that exist somewhere beyond the line itself? Well, I think that's a question for another journey.